Welcome to today's lesson. We are on Unit 1, Rates of Change, Lesson 6, the first principles of derivatives. The concepts you have explored to this point have laid the foundation for you to develop the sophisticated operation called differentiation. Now, differentiation is the process by which you will be determining the derivative of a function. Now, what exactly is a derivative of a function? Let's take, for instance, this curve. Now, let's say I was to draw a tangent on this curve at a specific point, and we know that the tangent, or the slope of the tangent of a line, represents the instantaneous rate of change at that point. Now let's take this tangent and move it along the curve. Okay, now what we notice is that it is not constant, it actually changes. Okay, so the instantaneous rate of change changes, the slope changes of the tangent as we move along the curve. Okay, so it can be represented as a function. So a derivative actually represents the function of a specific function. So let's take a look at the principles behind the first principles of derivatives. So the formula for the slope of the tangent at a specific point, which we're going to represent as m subscript tan, is equal to the limit as h approaches 0 for f at a plus h minus f at a, all over h. Now you'll recognize this as your average rate of change, just this part right here, except what we've added now is the limit as h goes to 0. So remember that as your increment of your interval gets very, very small and approaches 0, we get closer and closer to the slope of a tangent rather than a secant. And now that we understand limits, this will give us the slope of the tangent to a higher degree of accuracy. So the derivative of a function f at x now is a new function f primed at x, because the derivative is a function for any given curve, is defined by f primed at x, which is a notation that you're going to get used to, is equal to the limit as h goes to 0, approaches 0, for f x plus h minus f at x all over h, if of course the limit exists. Let's take a look at the first example. So example number 1, A, state the domain of the function f at x is equal to x squared. B, we're going to use the first principles definition to determine the derivative of f at x is equal to x squared. What is the derivative's domain? C, what do you notice about the nature of the derivatives? Derivative, let's just do that, there we go. Describe the relationship between the function and its derivative. Let's first take a look at number 1a, okay, in which we want to state the domain of the function f at x is equal to x squared. Okay, so our function f at x is equal to x squared. Okay, so I'm just going to give you a quick sketch because I think that'll help of the functions. We all know x squared as being a parabola, so I'm just going to sketch it quickly like this. Okay, this is your y, this is your x. Okay, so you'll notice that it exists for all values of x. So that means the domain is that x belongs to a set of real numbers, so XER. Okay, so B part we want to use the first principles definition to determine the derivative of our function. So let's first write down our definition. F primed at x is equal to the limit x is equal as h approaches 0, remember, and it's f at x plus h minus f at x all over h. Okay, so now let's fill in our definition or our formula with x squared. So I want you to write out the limit every single time until you actually evaluate the limit. Okay. So in this case, I'm not going to use my square brackets because it's fairly simple that I'm not going to get anything confused. Okay, so the limit as h approaches 0, and remember we're going to expand this, we can just go ahead and do that. And that's all over h, okay? So we can cancel terms. That x squared cancels with a minus x squared. And again, the limit as h approaches 0. And I'm just going to write what I have left. 2xh plus h squared all over h. Okay. My goal in these type of questions is always to eliminate an h from the denominator, or the h from the denominator, because if I was to evaluate the limit now, I'm going to get that the limit does not exist. Okay, so I always, doing these first principle type questions, always try to evaluate or to eliminate h. So the limit as h approaches 0, and I'm going to cancel, just going to go ahead and do this, okay, just to save us a little bit of time. Okay, here we go. And we're going to now evaluate the limit by subbing in 0. Okay, and that just leaves us with 2x. So f primed at x is equal to 2x. Okay, so our derivative is 2x, and our original function is x squared. Okay, so our exponent on the x in the original function is a 2. Okay, if we go to the derivative, the exponent on the variable is 1. Okay, so we'll notice is that the derivative has one lower exponent than the original function. Let's go on to example number 2. We want to use first principles of derivatives in order to differentiate f at x is equal to x squared. State the domain of the function as a derivative, graph the original function and its derivative on the same graph. Okay, so looking at A, number 2A. Okay, again, we're going to use first principles. So I'm just going to write out first principles definition. Okay, our original function is f at x is equal to x cubed. And again, the limit as h approaches 0 for f at x plus h minus f at x all over h. Okay, so let's use our original function and plug it into our definition or our formula. Okay, so now that becomes x plus h cubed minus fx cubed all over h. Okay, so let's expand the binomial. So the first term there is x plus h cubed. We're going to expand that. Now thinking back to functions. Now how did we do that? Okay, let's do a little side note over here. Okay, we use binomial expansion. Okay, using Pascal's. I know it's been a long time. Pascal's triangle, but hopefully it hasn't been that long. Okay, so what I'm going to do now is sketch out Pascal's triangle. And in doing that, remember we always start with 1, and then all the outer parts of the triangle is all 1. And then if we want to find the inner terms, what we would do is add the terms above it in order to get the next term. Okay, so that would be 2. And 2 plus 1 is 3, and 3. Okay, now I've just gone up to 3, but you can keep going. It's 4, 6, 4, and then 1. Okay, so each row represents the exponent. So 0, 1, 2, and then 3. Okay, and we only need 3. So we're going to use that row right there. Okay, so this is what I do. It's just my suggestion is you're going to take the coefficients and you write them out. First term, I just write them out on the second term as well. Okay, and then I just put plus signs in between them. Okay, you might be able to just go ahead and go straight to the answer. That's fine too, but this is just a little refresher. We start with the first term, okay, and that's an x, and that will start with the highest exponent, which is 3. Okay, 3. And it will decrement, so 3, 2, 1, 0. We take h, and it will start at 0, and we increase. Okay, and 3. Okay, perfect. Simplify. Remember, h to the exponent 0, anything to the exponent 0 is just 1. So that's just going to simplify to x cubed 3x squared h plus 3x h squared plus h cubed. Okay. Now we're simply going to go back to our question that we've been working on. Okay, and again, remember to write down the limit as h approaches 0. We don't want to drop that until we finally evaluate the limit. Okay, and I'm just going to replace an x plus h cubed with my expanded binomial there, expansion. Okay. Plus h cubed minus x cubed. Drop my little bracket there, okay. H, and we can eventually cancel out the x cubed. I'm just going to go ahead and do that. Okay, and rewrite everything that I have left. All over h. And remember, my goal here is to eliminate the h in the denominator. I'm going to cancel out. So each term has an h, so I can just cancel out. If that's confusing, factor out the h first before you cancel out the h. Remember, each term has to have the an h in it before you can cancel out the h, okay, in the denominator. So I'm just going to rewrite everything, what we have left. Okay. And every term that has an h in it will cancel out because we are going to substitute 0 into it. And that just simply leaves me with f prime at x is equal to 3x squared. Okay, so that's our derivative. Just for completeness, our domain for the derivative is xer, okay, because it is a quadratic, so it exists for all values of x. And our original function, x cubed, domain again, for next x cubed is xer. Okay, and that concludes 2a. Let's go on to 2b. Here I have a graph of both the original and the derivative of the function. Okay, in blue here I have our function, which is f at x is equal to x cubed. Okay, and you'll recognize that function. And in red we have f at x is equal to 3x squared, which is our derivative. Okay. Let's move on to part C. In part C, we want to determine the following using our derivatives function. Okay, so the first thing I'm going to do is actually write out our derivative, which is f primed at x is equal to 3x squared. Okay, and we want to evaluate the limit or the derivative at x is equal to -2. So I'm going to take -2, I'm going to replace x with it. Okay, so f primed at -2 is then equal to 3 -2 squared. Okay, so that's 3 and 4 and 12. Okay, and so we'll just do that with I as well. F primed at 0 is equal to 3, 0, and then we're just left with 0. It should be 0. F primed at 0. Okay, so part 3 will do the same thing. So maybe you can try this on your own as well. Freeze the video if you'd like, or go back to see if you've got the right answer. Okay, and it's just 3. Part D, we are to determine the equation of the tangent line that corresponds to the values you found in part C. Okay, remember that the tangent is a line, it's a straight line, so we can come up with an equation for it. So the first thing I do is write out the derivative, okay? So if we're looking for an equation of a straight line, okay, in slope-intercept form, remember y is equal to mx plus b, okay? An equation you know and love by now. Y is equal to mx plus b. So when we're trying to find this equation, we always look for two things. Remember, it's the slope and it's the b, which is the intercept, okay? And I want you to get good at these type of questions because you will see them again. Okay, so first thing, the slope. Remember that f primed at x, the derivative describes the slope. okay, at any point along that curve. Okay. So what we're going to do is, let's take one of those. Let's just do I. I think you get the point if we just do I. We were to, okay, let's go. Okay, so x was equal to -2. Okay, so that gives us our x. Now, how can we find our y? Well, our y, we can simply, let's see, I'm just going to write this out, is x cubed. Okay, so that means y, when x is -2, is -8. Okay, did you see how I did that? I said -2, -2 cubed then is -8. Okay, so I have x, I have y for when x is equal to -2. Okay, so now I need to find my slope. Okay, so we said that f primed at -2, and we've done this part already, is equal to 12. Well, at least I'm pretty sure we said that. Okay, so that means that that is the slope when x is equal to -2. Okay, that's our slope. Okay, so let's go back to our equation of a line. We have everything we need, okay, except for b. So let's find b. So taking everything we know here, okay, we're going to say -8 is equal to 12 times -8, oops, -2, plus b, okay? So that leaves us with -8 is equal to, that's a 2, -24 plus b. So then b is equal to, okay, so all I've done here is I'm going to leave, I've kind of swapped the equation a bit, so if I was to bring them over to the same side, plus 24, okay, so b then is equal to 16, okay, there's our b. Okay, so we have the two things that we need in order to come up with the general equation for the line. Therefore, and we always have a therefore statement, the equation of the tangent is y is equal to 12x plus 16, okay? We always want to give a nice statement at the end as well. Okay, so I just want to introduce you to a certain notation called Leibniz notation. Leibniz notation is used quite frequently, particularly in university. Most cases you will see both notations, f primed at x, as well as the Leibniz notation. I'm going to try and flip-flop back and forth so that you can get used to seeing both of those because they are used interchangeably. So not only was Newton the inventor of calculus, but also Gottfried Leibniz. So from that, he used a different notation, and it's named after him. Okay, so Leibniz notation expresses the derivative of the function y is equal to f at x as dy over dx. So basically, we'll talk further about this. Let me just introduce this to you. Leibniz's form can also be written as dy by dx, f at x, and which also notice here too, I couldn't do it with my equation writer. Okay, x is equal to a. Okay, that means that the expression dy by dx in Leibniz's notation means the value of the derivative when x is equal to a. So that's when it's evaluated. Okay, so what we'll also notice is that dy, delta, in Greek terms, okay, we just shorten it by saying dy by dx, but that's actually a delta in Greek. Delta actually means the change in. So the change in y over the change in x, okay? And that, again, is our slope equation. So it's the change in y over the change in x. That sort of helps me to remember that dy by dx is the derivative. So it's the change in. Let's take a look at example number 3. Now, example number 3 is an application type question. So the height of a javelin tossed into the air is modeled by the function h of t is equal to -4.9 t squared plus 10t plus 1, where h is the height in meters and t is the time in seconds. Okay, so that is our function right there. Okay, We want to A, determine the rate of change of the height of the javelin at time t, express the derivative using Leibniz notation, and B, determine the rate of change of the height of the javelin after 3 seconds. So let's first take a look at A. So an example number 1, or number 2 actually, A, actually I think it's number 3. So we're on example number 3, my goodness. Okay, so here we have the function that describes the height of the javelin. Okay, so remember you're throwing this javelin and it's doing this. So we'll recognize that as being a parabola. Okay, and let's see. Now we want to use the the first principles, but we're going to, instead of writing f prime at x, we're going to say dy by dx, the change in y over the change in x, is the limit as h approaches 0, f at x plus h minus f at x all over h. Okay, so this is not so nice. So we're going to use square brackets. Okay, so the limit as h approaches 0, okay, my square brackets, I take my entire function, and everywhere there's a t, because that is my independent variable, I'm going to replace with x plus h. So negative 4.9, using round brackets now, x plus h squared plus 10, x plus h plus 1. Yes, this will be long, okay? And that is simply the nature of these type of questions. Minus, square brackets, negative 4.9 x squared plus 10x plus 1. Okay? So what this negative sign is going to do is it's going to change all of the signs inside the bracket. And of course, all of that is over h. Okay? So remember the goal is to eliminate this h. So again, the limit as h approaches 0, negative 4.9 x squared plus 2xh plus h squared plus 10x plus 10h plus 1. Okay, and I think I'm going to go ahead and multiply that negative sign in, so negative 4.9 plus negative 4.9 x squared minus 10x minus 1, okay, all over h equals to the limit as h approaches 0, negative 4.9 x squared minus, okay, because I'm multiplying the negative sign with the negative 4.9 with 2, plus 9.8 xh minus 4.9 h squared plus 10x plus 10h plus 1 plus 4.9 x squared minus 10x minus 1 all over h. Oh my goodness. Okay, so let's see. Let's use a colored pen for this. Okay, I'm going to start to cancel terms. So one of these with one of those. I don't even think you can see the color. And I have, oops, yeah, that's right. This with that. Anything else? The ones. And that looks like it. Okay, so rewriting the limit as h approaches 0. Okay, so I have minus 9.8 xh minus 4.9 h squared plus 10h all over h. Okay. And I'm going to cancel one of these with one of those. And that just leaves me with now the limit as h approaches 0 minus 9.8 x minus 4.9 h plus 10. Okay, so this term goes away when we actually evaluate the limit. So dy by dx is then equal to minus 9.8x plus 10. Okay, and that's our derivative.